Welcome to the pre-recording of lecture 29. In this lecture, we go back to geographical information systems, and we look at the problem of zooming in to a map. The entire chapter 10 in our textbook is dedicated to these windowing queries. In the lecture 29, we focus on a simpler case where we consider intervals, and we will see how to pre-process the intervals in a tree, which makes the queries very efficient. Okay, what's our problem? Well, what we want to do is to zoom in onto a window. So here we have a map with line segments. So you can think of those as a map with streets, horizontal and vertical. We want to zoom into this. So the query region is zoomed out a little bit larger, shaded in green, and we want to report all the data that is in that window. Our problem is to do this quickly, and with that we want to store the data in a way that allows us to zooming in quickly. Okay, so you must have done this if you have used an electronic map. You have a map of a whole city and then your place where you are, and you want to zoom in to the most neighboring streets, trying to locate your position, where you have to go to next if you get lost. So we have already spent some time with queries and geographical information systems. So this is a slide which I copied from an earlier lecture. So in green, in yellow is our region of interest. So that is the rectangle x colon x prime, the horizontal stretch, and then there is the vertical stretch y colon y prime. So that is the range. Now the region, so the plane is actually subdivided along these points. So we bisected the region into alternatingly choosing a horizontal, a vertical, and a horizontal line, splitting each time the data set in half. So in green um, are the nodes 5 and 7 that actually are overlapping with the query region. So earlier this is, you could see this as one way. So the yellow region would be the region where we want to zoom in. And with a balanced binary tree, which is a range tree, we can look in time log n on the x coordinate, and then also log n on the y coordinates, where n is the total number of points that we have. So we have a complexity of log square of n. We can reduce one of the log n factors with the technique of fractional cascading. So instead of having to do two binary searches, we can get by with one by linking sorted arrays. So we have two sorted arrays here, A and B. If they are linked, then we can save one binary search. So we addressed this earlier with range trees. So range trees are also multi-level data structures, as we introduced earlier. We have a query time that is output sensitive, so we have the factor k there. If your range is large, then it will take longer, but our if the k is very small, then actually it will go very fast, almost in constant time, in as the cost of a binary search on n data elements. Okay, so that is the problem, and that is what we have covered so far. So let me specify what the problem really is. So we have a query window, very similar to the range as before. So we also are using two intervals in the x and the y axis. So we want to report all the segments. The segments are represented by the endpoints. So if we can grab the points, so we can make these range trees based on the endpoints of the segments. If we can grab the endpoints, then we know which segments we have to report. So with range trees, we can do this in n log n. So the cost for these data structures is n log n storage, and also the pre-processing time. We cannot do better than the cost for sorting. And the search time is actually, I think that might be an error here. So it's not n log n. So, but this n here has to be removed. So range trees are used are multi-level data structures to store points. But if we are having, say, horizontal or vertical segments, can we actually do better? So in this lecture, we focus on storing intervals, not just storing points. And with our pre-processing, the data structure that we will be building, so the balanced binary search tree that we will be building, we will be able to reduce the cost from n log n storage to n, which is a significant factor. Okay, so here is our problem. Perhaps we can just look at the picture. So we have a collection of intervals given, a set of intervals. We arrange the intervals. So here, if you look from left to right, so every interval to the left is copied to the right. But by computing the middle, or actually the medium between the endpoints, between the most left point of all the intervals and the most right point between the intervals, we partition the set of intervals in three sets. There are the intervals that contain that medium. And these are the intervals that we store first. So you can kind of recognize a tree structure in there. We have the intervals that contain that medium, and then all intervals that are to the left and all intervals to the right. So if we do this, then a tree comes up very naturally. That will be used to pre-process a set of n horizontal line segments. And if the tree is balanced, then the search cost is proportional to the depth of the tree or the height of the tree, and that is logarithmic in the number of data elements. Okay, let us define the steps. So in making the nodes, we have to do this partitioning. So we compute the medium and then we classify every interval. So we have all the intervals to the left, the intervals to the right, and then the intervals that contain that median. So that's it. Okay, so how do we then efficiently query it, this data structure? So we have a query line. So in some sense, this is also called a stabbing query. So you actually want to know all the intervals that contain or that are intersected by the line. Um, so what do we have here? Um, we have the um, stabbing of the intervals. How does the algorithm work? If we are actually the medium, then we have to report all the intervals that contain it. So that's actually a base case. Um, if we are at the left, we report everything at the left. If at the right, we report everything to the right. But also we have to investigate the middle. So here, notice that it might not be entirely correct. It may be a subset. So here we have an interval that is containing the median, but actually it is not really containing the line with the query point. So one may have to be a little bit careful. Okay, so how do we store now the intervals? We have to compute the medium. So we have all the intervals that contain the medium. And then we will sort on the left and the right points. We will need to sort because we had this case where we do not need to report all the intervals in the middle. So we will store all the intervals twice. It may be redundant, but 2 is still a constant. So the storage cost will still be ON. So the tree structure will actually ensure the logarithmic um, cost in n. Now, of course, if we have that all the intervals are actually tightly grouped together or overlapping each other, then actually each time we may report many of them or all of them. So this is where the output sensitive factor k comes in. Okay, so we sort the intervals on their left endpoint. We sort the intervals on the right endpoint. And this will be stored at the left and the right. Um, so uh, we have the left and the right, but that is actually stored at the node. So it may be a little bit too premature to actually go to the um, left and right children. So that's actually the purpose of the um, exercise. That you realize that what is stored at the nodes is this left or the right, these two lists that are stored. It's not, and this is for all the segments or all the intervals here that contain the median point. Okay, complete this recursive structure. So on solving this interv exercise, you see you have 6 more intervals. So you will label them as 6, x7, x8, and then also 9, 10, and 11. Um, so and then describe what are the sorted um, sets, the lists that are stored at these two children. Okay, here is the construction. You see what we store at the node. So this is actually the important step here that relates to exercise um, one. So what we store are these two lists. So the fancy L stands for a list. So we store all the lists sorted. So actually we store the intervals twice, sorted at the left and sorted at the right point. That's important again because when we report, we will then very efficiently run through those lists from left to right, or if the query points is to the left, or from right to left if the query point lies to the right. So we may not need to report all the line segments. Okay, so computing the medium in step three, partitioning or splitting the intervals, and then recursively continuing after making the nodes. So the node consists of the data at the node, so this is the V. Then we have the two subtrees, the left and the right child, which are constructed recursively. So it's a divide and conquer algorithm. But the cost for this is always in the sorting. So we have the sorts that need to be done, actually also two sorts here in step 5. But it's still, the 2 is still a constant, still n log n. Okay, what is the cost here for this simplified problem? We have the depth that is logarithmic. At every node, we have at most half of the intervals. So each time we actually split the data set in half. So the total number of nodes that we have um, equals, it should be equals uh, n nodes, and because we store the lists twice, we have this factor 2n here, but it's still on. So the trees is some sense balanced here. That's because we are splitting on the median. Um, it could be that, so I think you have to think about this a little bit. Where would it go wrong? And you should actually verify that the depth is indeed logarithmic in the total number of line segments. It could be much less than logarithmic. You see, for the example on that we have been using, we had 11 intervals, but the depth was only 2. So, and the logarithm of 11 is more than 2, more than 3. So it's an upper bound in some sense. So you would have exactly the logarithm of n if the intervals are actually very tiny. So you can think of intervals that actually are just like points. That's actually the worst case scenario here. Okay, the other lemma is that because this is a divide and conquer, the um, cost of the algorithm to construct this interval tree is n log n, and that's because of the sorts. Um, okay, how do we query an interval tree? Well, here is the picture again. So we have our stabbing, so the vertical line that goes to this QX. You see, we are going to run the, so what is important here is that QX is at the left of the medium. So we are going to look here first. So we're first going to report S5, S2, um, S1, S4, but we are not going to report S3 because all the intervals are sorted on their left. And we see here that the left point of S3 is to the right. So we are, and it's not actually intersecting. So that is the query in the middle. Oops. Um, but then we have to continue because we should also report this line segment here. Okay, let's try to formalize this now in an algorithm. So it's a recursive algorithm. It starts with the node of an interval tree, which starts at the root. But you can see from the recursive calls, we're going to the left or we're going to the right child. So we are going to either walk the left or we're going to walk the right. Depending on whether the so it doesn't really matter if we are really at the middle. So then we just walk the um, intervals that were stored at the node from right to left. And in some sense, we will actually report all of them. So there could be um, an optimization here. If it is actually equal, then actually we have to report all the intervals that are in the left or that are in the right. But it's still linear, so this optimization will not save us anything in some sense. We have to, well, in some sense, if we have to report everything that is intersected, then actually we don't need to do a recursive call. So that's actually what we would save if we have this optimization. But for simplicity of the algorithm, it's nicely symmetric. Okay, so this will be a search that has a logarithmic cost because the depth of the interval tree is logarithmic in the total number of intervals. So with each time we report a number of intervals and the sum of all the intervals that we report equals k, and that is linear. So the main result then of this lecture is stated here. We have a linear storage, linear in the number of intervals. Because of the sorts of the endpoints, it takes n log n time. In some sense, we could do the sorts once and for all, and sort all the intervals and then select from those lists, from those sorted lists, preserving the order. And the queries are logarithmic and output sensitive. Okay, so that's the main theoretical results. Let us now go to the practice. So let's look at running an example in Seagull. So I should actually say that, let me first flip to the documentation in Seagull. So you see here that the relevant package is the interval skip list. And if we look at, so you can actually already see here the terminology. So we do a stabbing query. Um, so the user manual has two examples. I will only illustrate the first example. The second example actually illustrates how you get to these intervals. So I said in the very beginning, you can imagine that these intervals are streets. But you can also think about height interpolation. So actually you have a model of a terrain and you want to take a segment with a minimum height and a maximum height. So this is more convoluted because it actually uses a Delaunay triangulation to model the terrain. So I will not discuss here. What I will illustrate is the first example. So let me go back to the slides. So I'm running the slides on a Windows subsystem for Linux, and here are the installation instructions again. The example set is downloaded separately, and if one looks at the examples, one sees the interval skip list folder, and that contains the intervals code. So let's run it. So I have make file. So this shows the compilation instruction, and the number of intervals is I think n equals 10. So this is the range of the numbers, and then the depth of the tree might be 3. So here you see how the intervals are constructed with the queries. Actually, there are n intervals. So let me show the code again. The code is quite simple, at least if you are a little bit familiar with the C++ uh, syntax. So we have 10 intervals, so you can see the making of the intervals with the endpoints I and I plus D. So D is not the depth of the tree, but it's the width of the intervals. They are inserted at random. Um, that's an important point here. It could matter. So the textbook does not mention randomized algorithms, but the algorithm to make the algorithm that is implemented in Sigal is actually incremental. It's not our divide and conquer algorithm that we have seen. Um, So nevertheless, I hope it's also very efficient constructing and updating the data structures. So you see that there is a print that is going on after the finding of the intervals. And then it removes the intervals. Okay, so then this next exercise um, asks to um, see whether the time is actually n log n. Um, you can eventually also try to remove the randomization and see if it's then is still n log n. This is a side step, but we have discovered in this we have at least three different problems. We have discussed randomized incremental algorithms. In some sense, Sigal here presents another randomized incremental algorithm. Um, do you observe the n log n um, cost as the number of n? So you might go up to a million. Um, n log n algorithms are still fine for very large inputs. If it's not randomized, if it's going to be quadratic, then the million intervals could cost you. Okay, um, let's go more to the original problem. So what if we would actually step now with not with one coordinate, but where we have two coordinates? So we have a query window. Um, so the window is here. So the original problem that we want to solve um, is this green window here in the input. But what we will first consider is that we will do a limited stabbing query, where actually when we stab, we don't go all the way, but we only consider um, the heights essentially. So can we run directly the query of the interval tree on the example shown above? We can do that, but now actually for every interval we have a height as well. So what happens when we run this, and in some sense, what do you expect of the running time? So the running time will still be logarithmic in n, but it will be the k that matters. In order for the algorithm not to report too many intervals, you will need to place a filter. So what you will see is that it will matter a lot if the windows, or if actually this red segment here is actually relatively small compared to the entire line. So you can see that for the example, so you can also on the example shown above, so what happens? Well, you have two segments here and you have this segment. So of the reported segments, so here you will now only report 2 instead of 5. So that's the plain answer to this. But you see that the k in the output is actually significant. So it could be that the output is cut in half. And this justifies the investigation of other data structures. So here you see the application of range trees again. So we started in the first part of this lecture with range trees. So what do we have for a range tree? So we will store the sorted lists contained the endpoints, but actually now we have intervals that also have a height. So not only um, left and right, but the intervals are also situated at a certain height. So we have a second coordinate, and in a range tree is a multi-level data structure. So you have trees for the x level, but then at every node you have another tree for the y coordinates. So applying the results that we have considered quite earlier in this course. So we can construct range trees by two sorts. So it's still n log n. The storage cost is also n log n. And the query time is quadratic in n if we don't use this fractional cascading technique. So that is the result. So I'm actually finishing a little bit earlier. So we considered the problem of zooming in into a window, and our segments are horizontal. So we have n horizontal line segments. Storage and construction cost are n log n. Query cost is square in the logarithm. So um, that is where you want really the k in the output size. So if you are actually relatively confident that the k is not an important factor, then actually the interval tree might be quite a proper structure, proper data structures to solve this problem. Otherwise, we go back to our range trees. Okay, perhaps I can end again with the documentation of the interval skip list. So the terminology of stabbing queries. Um, so there is this randomized list structure, and this is where the skip list comes in. We have covered Delaunay triangulations in the previous chapter. So the invitation for this second example would be to interpret what this example actually represents. So we construct a Delaunay triangulation. So with every point we have coordinates and we also have heights. So the third coordinate represents a height. So you can ask for all the intervals at a certain height. So here you see the elevation that ranges between 0 and 10 and 0 and 100. And then we use the number 50 in the searches for the intervals. Okay, run this example and see what comes out. It constructs um, Delaunay triangulation. So here you see the incremental construction for the Delaunay triangulation for a three-dimensional data structure. So something point set, something that we have actually not covered in the algorithms on the previous chapter. Okay, the purpose of this course is that you understand what the problems are in the textbook, that you can read the textbook, also you get better prepared for the exercises in the textbook. So in exercises 1, 4, and 9, they are selected that they all deal with interval trees and the interval problems. So in the next lecture, we will discuss priority trees. Priority, so you can sometimes see the intervals as time windows. You have a deadline, but the deadline is often a target, but then you have the hard deadline at the end. So there are problems with scheduling that are also important applications for this. Okay, I stop here. So we still have 2 more lectures to go before we start reviewing for our second midterm, and then we close off actually chapter 10 in the textbook.